Hi guys. So in lieu of having a Zoom call, I'm just going to be doing this pre-recorded lesson. So as you see here, I've got some notes written down and I'll scan the lesson notes from this video as well, so you can just refer back to it later. But yeah, just got some pre-written notes, and what I'm going to be doing in this video is just going through a couple of examples from exercise 10F and 10G. And of course, this being a pre-recorded video, you can go back and pause and all that stuff as you're going through. So yeah, first of all, we're talking about tree diagrams, and this is kind of like a continuation from, I think it was like exercise 10B. And I mentioned back then, like the tree diagrams do get a little bit more complicated, and this is what I'm talking about. So probabilities of events can change between stages in a multi-stage experiment, and so these need to be reflected in the tree diagrams. What we mean by that is, if we're doing with and without replacement, or like without replacement, you can change, like the probabilities in each branch might be different. And then also we can be using our addition rule and our multiplication and our product rule for probability as well to, solve other problems that kind of come up with these tree diagrams. So let's just start off with exercise examples. Exercise 10F. And I'll just start off with, let's just have a look at question 6. So question 6, all right, we're told that the probability that a set of traffic lights will be green when you arrive at them is 3 out of 5. A motorist drives through 2 sets of lights. Assuming that the 2 sets of lights are not synchronized, find the probability that blah, blah, blah. So what not synchronized means is, like, if it's 3 out of 5 for the first, it's not going to be like you're not going to get in the first and the second. So let's just start by drawing a tree diagram. And as always start with a single point, okay? And then we'll branch off into the 2 things. So the first stage is the first set of lights, okay? And basically, when you go into this first set of lights, there's 2 things that can happen. So 2 branches. You can either, it'll be either green or red. Now, of course, in real life, you're talking about it could be green, amber, or red. But the question's only specified green. So that means we're kind of considering red as basically not green. So it's either green or not green. So I'm just going to refer to that as R, but it doesn't really matter. And of course, we're going to add the probabilities. So we're told that the probability of it being green is 3 over 5. So this is also 2 out of 5. All right, because of course the probabilities need to add up to 1. So this represents the first set of lights. And then going into that second set of lights, we now have 2 possibilities for each. And in this situation, there's actually no change to the probability. This is still going to be 3 out of 5. And this is still 2 out of 5. This is still 3 out of 5. This is still 2 out of 5. So nothing's actually changed between each stage, but you'll see why I've chosen this question in a second. So here we have GG, GR, RG, and RR. And of course, we can find the probabilities of each of these as well by just multiplying the fractions. So we're doing green and green. So remember, we talked about whenever you think of the word and, it's multiplication. So this will be 3 over 5 times 3 over 5, which is 9 out of 25. This will be 3 out of 5 times 2 out of 5, so that's 6 out of 25. This will also be 6 out of 25, and 2 times 2 is 4 out of 25. Now, to make sure that we've got those numbers correct, of course, if we add up all these probabilities at the end, it should equal 1. So 9 plus 6 plus 6 plus 4 equals 25, which is 25 out of 25. This is why I kind of suggest that you, when you're multiplying these fractions during your tree diagram, I generally suggest that you don't simplify these fractions. You can't actually simplify these ones anyway, but keeping them all as the same denominator just helps with your adding and solving the questions later on. So anyway, 6A is asking, so find the probability that both sets of lights are green. Well, that's pretty easy. We're just looking at probability of GG, which we've already found here. That's 9 out of 25. So that's a pretty basic one, but looking at question B, and this is why I chose this one first. And The reason why I chose this one is we want to find the probability of at least one being green. So probability of at least one green. Now, for the probability, at least one means that you can either have one green or two greens in this situation. And of course, what you could do is just look at where all the greens are. So it'll be this, this, and this. And what we're talking about is a probability of green, green, or green, red, or red, green. Remember, we talked about whenever we think of the word or, we add. So we'll be doing 9 plus 6 plus 6, which is 21. So we're basically finding the probability of these three. So 9 plus 6 is 21 over 25. Now that's one way of doing it, and if you have a pretty easy set like this, that's pretty good, because you can just be like, okay, well, it's this one, and this one. But you can imagine if there was just like a bunch of different, if there was like more than 4 outcomes here, it will be hard for you to calculate each one of these. So another way to do these, when it says at least one, so the probability of at least one, let's say at least one A, okay, so the event being A, well, that equals 1 minus the probability of not A, okay? And what that means, when you think about it, that kind of makes a bit of sense. If we're saying that, the probability of at least 1A, that means I was about to say at least 1A, like it happens at least once. So the complementary event to that would be no A's happening. Okay, so the probability of no A's happening, or in this case no greens happening, is red, which is 4 out of 25. So we're only looking at one outcome, rather than looking at 3 outcomes. And this is going to make things a lot easier when we have a lot more outcomes, because now we can just do 1 minus 4 over 25, which is 25. So looking at this case, we could say that this is going to be 1 minus 4 over 25, which does equal 21 over 25. Okay, so that's the other way that you can do at least one. And like I said, in this question, yeah, it's a bit easy to just look at these 3 things and add them up, and that's fine. But there's going to be other questions where having to do it this way is going to be a lot more useful. So let's look at another question. So let's look at question 13, because I think that covers a lot of different types of questions you can be asked. So question 13, it says, in an aviary, there are 4 canaries, 5 cockatoos, and 3 budgerigars. If 2 birds are selected at random, find the probability that both the canary, and then we'll go to that. So let's first of all start with our tree diagram. When we say if 2 birds are selected at random, what we're kind of suggesting is you can't choose the same bird twice. Okay, so that means we're doing it without replacement. So let's first of all draw a tree diagram. The first stage is us choosing the first bird, and so that means we've got 3 options for the first one. And so this diagram is going to get a bit wide. All right, so the 3 options, we got canaries, we have it's a bit annoying. I'm just going to say T for cockatoos, and 3 budgies. Okay, so canaries, cockatoos, budgies. Generally, questions are written in a way that they all start with a different letter, so it just makes it a bit easier, but whatever. So in an aviary of 4 canaries, 5 cockatoos, and 3 budgies. So that means there's 12 in total. All right, so 4 plus 5 is 9, plus 3 is 12. So the probability of choosing a canary first is 4 out of 12. The probability of choosing a cockatoo is 5 out of 12. And the probability of choosing a budgie is 3 out of 12. So we've now chosen our first bird. And now for the second bird, we now have 3 choices again. And it's not saying, like at no point in the question did it say a different bird is chosen. Like as in like a different type of bird, but you can also assume, well, it's not going to be the same bird twice. So we've got CTB, CTB, CTB. All right. And that means our sample space is CC, CT, CB, TC, TT, TB, BC, BT, and BP. So we've got 9 outcomes. And remember from the other day, we talked about that the way that we can calculate exactly how many outcomes there are going to be straight away is there were 3 options in the first stage, and there were 3 options in the second stage. So 3 times 3 is 9. Okay. Now, we also need to consider that these probabilities are going to change. So if I chose a canary in the first one, that means it's going to be 3 out of 11 for the second one. This will be 5 out of 11, and this will be, what's that going to be? That's 3 out of 11. And we can start finding out probabilities from this, so canary and canary. So again, this is where I talk about, don't simplify your fractions when doing this because it just makes it a little bit more difficult. So 12 times 11 is 132. And 4 times 3 is 12. Now we can simplify that. That will be 6 over 66. And that will be 1 over 11. And that is fine. But I suggest you keep it as with 12 over 132. Because when you get the rest of these probabilities, they can all be out of 132. And it's easier for you to manage. So we have 20 over 132. And we have 12 over 132. Now, I could go through and find the probabilities of the rest of these, but what you can actually do with your tree diagram kind of just written there, you don't actually need to draw, find all the probabilities. Just look at what the question's asking you and then focus on those probabilities. And honestly, once you get good enough with these kind of probability questions, you might not even need to do a tree diagram. So looking at 13A, of course, the question might ask you to draw a tree diagram, and then you would have to anyway. So look at 13A. The question's asking, what's the probability that they're both canaries? Well, we've already got that one. We're looking at probability of C and C, or CC. And that's just going to be 12 over 132, which does equal 1 over 11. When you're actually answering your question, you should simplify. But when you're doing like the calculations or the tree diagram here, no need to simplify. I think it makes it easy if you don't simplify. So that's that first question. Second question is if neither is a canary. So probability if neither canary. Well, what we can do, if neither is canary, what we're going to do here is going to find all the ones where there's no canaries involved. So we can't choose that one, not that one, not that one, not that one. This one, this one, this one, and this one. So we're looking at these 4 outcomes. Now, of course, it's not just going to be 4 out of 9. What we're going to need to do is look, if neither of a canary, we need to be looking, so neither canary means also probability of at least one canary. As the complement of that, because if you find the probability of at least one canary, then it's none of that. So that doesn't really help what we're doing here, but I'm just going to point that out there because you could write it as that as well. But in this case, there's no real quick way to do it. All we need to do is just look at all the cases where it does work. So the probability of T in this one would be 4 out of 11. And this is what I'm saying. You don't need to do all these until you actually need to. That makes sense. So the probability of TT, so choosing a cockatoo and a cockatoo, so that means like neither of them is a canary, is 20 over 132. And this will be 15 out of 132. Okay. And then I'm also looking at BT and BB. So this would be 5 out of 11, and this would be 3 out of 11. So this will be 15 out of 132. And this will be 9 out of 132. So looking at this question now, if neither are a canary, that means we're looking at this one, we're looking at this one, we're looking at this one, and we're looking at this one. So anything that has a C, we're not going to be looking at. So this is the advantage of having them all over 132. Rather than me having to add 4 fractions together, I can just do 20 plus 15, which is 35, plus 15, which is 50, plus 9, which is 59. So I know it's going to just be 59 over 132. All right, this is the advantage of having the probability, the denominator the same. You can just add up the numerators. And 59 over 132, pretty sure that doesn't simplify 59 as a prime number. Looking at question C, the question is saying one is a canary and one is a cockatoo. So one canary and one cockatoo. Well, what we need to look at here is, note that the question isn't saying a canary then a cockatoo. It's just a canary and a cockatoo. So that means we're going to be looking at CT and also TC. So we need to find the probability of this TC. So that's going to be 4 out of 11. So that's going to be 20 out of 132. So we're going to be doing 20 plus 20. So that's going to be 40 out of 132. And then if you simplify that, I believe that'll be 20 over 66. And then that can simplify further to be 10 out of 33. And you can't simplify any further than that. And lastly, question D. So question D, we have at least one canary. So remember the quick way to find at least one canary. Well, we've already kind of, so at least one canary, just like what we were talking about at the on the other page, we said that the way that we can do at least one is we just do 1 minus the probability of no canaries. And we just found that in part B. So that's just going to be 1 minus 59 over 132, which we can just do 132 minus 59 is 73. So it'll be 73 over 132. Now you can check this, but if you're looking, trying to find all the ones where there's at least one canary, that means you're going to be doing that. So anything with a C. So that plus that plus that plus that plus that. And if you do 12 plus 20 plus 12 plus whatever that is plus 20, you'll find it to be 73 of 132. But the idea is, because we're doing at least one, you can just do 1 minus none of them. And that's how you can find that out quicker. So that's kind of a question where the probability has changed, and we're also thinking about like all these different compound events. All right, so that's that for 10F, and I'll just quickly go through 10G, which is a bit quicker, or like makes a bit more sense, but it's also a few more notes, so I'll read through these. So we're talking about conditional probability here, and this is just when we're talking about, we're limiting a sample space of an experiment because we're trying to meet a particular condition. So we'll read through this. So sometimes we consider events with particular conditions, thereby removing some outcomes from the original sample space. So what we mean is, like, we could be talking, I've got an example here, but another example could be if we're drawing a card from a standard deck. So our sample space has 52 elements of it in it. So the cardinality is 52. But like a condition could be, knowing that it's a red card. And now instead of thinking about the 52 cards, we're now limiting it to 26 cards. Okay? So so for an example here, find the probability of choosing a girl, like say you have like this group of students, find the probability of choosing a girl out of the students that are studying economics. So given that that person is studying economics. So in the above example, the original sample space could be all students. What we mean by that is, originally if I'm just finding the probability of choosing a girl from a group of students, say like it's year 11 class, so 11 grades, that's 42 students. But now that I've got this condition but it has to be a student studying economics, we're now going to limit that sample space down to however many students do economics. I'm not sure of that on top of my head. But yeah, like by adding that condition, we're now reducing that sample space. So it's still those same students, like the students studying economics are still within those 42 students in year 11, but now we're limiting that sample space. So in this case, we can consider the set A is all the girls in the grade, and the set B is all the students that study economics in the grade. This event would be written as A, whatever that you want to write, say that the symbol is B. So it's not like a dash, it's like a absolute value sign, really. And that's read as the probability of A given that B has occurred. So looking at this, like, what's to find the probability of choosing a girl such that they, like, out of the students that are doing economics. And this can be calculated. So the way that we can find this is the probability of A given that B has happened. You can find the probability of A and B happening. So in this example, you're looking at the girls that study economics. So whatever that is. And then divided by the probability of people that study economics. Now you're going to find that this formula might be helpful in some cases, but what you're actually going to find more likely is when you're doing questions, you can kind of just remove things from your sample space intuitively and just solve the question from that. So with that, let me just do a couple of examples of this. So from exercise 10G, let's look at question 3 first of all. So question 3, we get given a two-way table, something that you might not have seen in a while. So a student is investigating if there's a relationship between those who choose Mathematics Extension 1, known as M, and those who choose English Extension 1, labeled as E. So looking at this, and I'll just quickly draw up the two-way table. So we have M, and then remember with these two-way tables, it's always like not M. So in the book, it's referring to as M bar, and that's fine. We have E, and then not E. E being like they do English extension. And then remember also with these two-way tables, we have totals as well. And in this, we're told that this is 29, this is 95, this is 27, and this is 42. So first of all, of course, what we want to do, like it says in question 3A, is we want to complete the table by filling in the totals, and that's pretty easy. So here we'll just do 29 plus 27 is 56. 95 plus 42 is 137. 27 plus 42 equals 69. And 29 plus 95 is 124. And then to find the total, we'll do 193. Did this, and of course if I do 124 plus 69, it's also 193, and that needs to happen, of course. So find the probability that a particular student chose neither mathematics nor extension 1. So in this question, it's saying they chose neither this nor that, so we're looking at this, but the question hasn't given any conditions, so we're going to be looking at the total. So for this probability of neither E nor M, that means we're looking at this number, so not either, so it'll be 42. I have 193, making sure that we're writing as a probability. We're asking for the probability, not just the amount. Part 2 is find the probability that they chose English Extension 1, given that they chose Maths Extension 1. So this is what we're talking about here. So we're doing probability of E, given that they did M. And that's what we're saying with the notation here. So E out of the ones that did M. So looking at the first of all, we need to think about the denominator. So we're not only just looking at these 193, we're looking at these 124 people. So out of the 124 people that are doing Maths Extension, 29 of them are doing English Extension as well. looking at part 3. So Maths Extension 1, if it is known that they choose English Extension 1, so it's kind of the opposite. So M given E. So now we're looking at the 56 people that did E. We've got 29 of those that are doing M. And then lastly, Maths Extension 1, given that they did not do English Extension 1. So we can write that as P, M, E bar. So the probability that they didn't do English Extension is 137. And the ones out of those 137 that don't do English Extension, 95 of them do Maths Extension. So that's that. Well, we can just, going forward a little bit, let's look at question let's look at question 15. And in this question, I'm going to try to do it without a tree diagram or anything like that, just going straight into the numbers. So question 15 is that a card is drawn from a standard pack. The dealer tells the players that it is a court card, Jack, Queen, or King. And that kind of narrows down. So here we have like a card is drawn from a pack. So originally you'd be thinking about 52 cards. But now that we're told that it's a court card, Jack, Queen, or King, that means we now only have 12 cards. We've now restricted our sample space straight away. So what's the probability that it's a Jack? Well, there's 4 Jacks, so it's just 4 out of 12. Pretty simple. What is the probability that it's either a Jack or a red card? So out of the 12 cards, 4 of them are Jacks. Okay, so probably 4 of them are Jacks. So Jack or red. Remember, the way that we can find this is the probability of Jack plus the probability of red minus the probability of Jack and red. Because remember, we don't want to double count these. So the probability of drawing a Jack out of the court cards will be 4 out of 12. Probability of drawing a red card will be 6 out of 12. And then the probability of choosing a red Jack, so that means you're choosing the Jack of diamonds or the Jack of hearts, is going to be 2 out of 12. So 4 plus 6 is 10, minus 2 is 8. So we have 8 out of 12. And then lastly, what's the probability that the next card drawn is Jack? Assume that the first card was not replaced. So what we're assuming here is that the probability that the next card drawn is a Jack, you're assuming that the first card was a Jack. So now there's going to be, out of the 11 cards, because you're again told that it's a court card, but now there's 1 less, and we're told that it was not replaced, and now there's only 3 Jacks left. So yeah, I'm hoping that you're seeing that this conditional stuff isn't too difficult. It's just limiting the sample space. The main thing is just looking at this notation, because the question could easily just say find P/E-M or whatever you want to call it, and you would need to know what that means. Anyway, this video has gone for a bit long now, so maybe, not good to say it now, but play it at 1.5 speed or something so you can go through it quickly, and hopefully it's been helpful. Sorry for the delay on this, and like I mentioned, tomorrow we're going to be doing a quiz on probability in our class, so please be there for that. Thanks.